Hi, Steve here. I'm going to tell you about our paper, Proper Learning, Helly Number, and an Optimal SVM Bound. This is joint work with Olivier Bousquet, Shay Moran, and Nikita Zhivotovskiy. So here's a high-level overview. A few years ago, the optimal sample complexity of pack learning was determined to be VC dimension over epsilon plus 1 over epsilon log 1 over delta. This refined the classic upper bound for ERM by a log factor. But the algorithm achieving this was what's called an improper learning algorithm, which means it can output a hypothesis that's not in the concept class. So that leaves the question, when can the optimal sample complexity be achieved by a proper learning algorithm, meaning it always outputs a hypothesis in the concept class? So that'll be the first part of the talk. In the second part, we'll look at a specific question for the case of linear separators. We'd like to know whether specifically the support vector machine achieves the optimal sample complexity for learning linear separators. This is a classic open question dating back to the early work of Vapnik and Chervonenkis and has received some significant attention over the years. We find answers to both of these questions. For the first question, we identify a complexity measure which distinguishes between classes that can be learned optimally with a proper learner and those that can't, aside from some caveats I'll mention. For the second part, we'll actually completely resolve this classic open question and find that indeed SVM does achieve the optimal sample complexity for learning linear separators. In fact, this result follows from a general theory we developed on a special type of compression scheme called a stable compression scheme. This general theory also has other implications. For instance, it also implies that maximum classes can be properly learned with optimal sample complexity, which wasn't known before. Okay, so let's get into the details. We've got sort of the classic pack learning setup. So there's an instance space X, there's a label space Y, which is just 0 and 1, and there's a concept class C, which is just some set of classifiers. There's an unknown distribution P on X, and there's a target concept F star in the class. And we define the error rate of a classifier H as just the probability it disagrees with the target concept on a random point from P. We can define a learning algorithm as taking any number n of IID samples with the corresponding target function values and outputting some classifier H hat. And we'll say the algorithm is proper if H hat is always guaranteed to be in the concept class. So for any algorithm, we can also define the sample complexity of that algorithm as the smallest sample size n, such that for any distribution in any target concept in the class, the error rate of H hat is less than epsilon with probability at least 1 minus delta. So I'll just give a bit of background here. The classic approach to proper learning is a technique called empirical risk minimization, or ERM. The idea there is simply output any classifier in the class that's correct on all of the data. The classic analysis of Vapnik and Chervonenkis showed that any ERM achieves a sample complexity of VC dimension over epsilon log 1 over epsilon plus 1 over epsilon log 1 over delta. Now, as I mentioned, we know that the optimal sample complexity is VC dimension over epsilon plus 1 over epsilon log 1 over delta. And so you'll notice that there's an extra log factor in the ERM sample complexity bound. And actually, it's been known for some time that this is not just a loose analysis. There really are scenarios where ERM is suboptimal by a log factor. And this issue is now very well understood. But it does leave open the question, what about analyzing particular proper learners that go beyond the general analysis of ERM learners? Okay, so we're going to define a complexity measure to identify which classes allow the optimal sample complexity to be achievable by proper learners. And we'll actually work with 3 different variants of the complexity measure. So the first one is called the dual Helly number. It's defined as the smallest k such that any unrealizable set has an unrealizable subset of size at most k. This has a direct connection to a quantity called the Helly number, which comes up in the analysis of convex sets. The second quantity is called the hollow star number. It's defined as the largest finite k for which there exists an unrealizable set of size k, such that if you flip any one of the labels, it becomes a realizable set. This has a direct connection to a quantity called the star number, but actually the hollow star number is typically much, much smaller than the star number. The last quantity we'll define is called the projection number. This one's a little more complicated to state, but it turns out to be very useful. So first, for any C prime, a finite subset of the class, let's define this set X C prime K as the set of all points where more than a 1 minus 1 over K fraction of C prime agree. And then define the projection number Kp as the smallest K such that for any C prime, the classifier that's the majority vote of the C prime classifiers has a realizable classification of that set X C prime K. So that's the definition. And I say it's useful because it actually comes with an associated operator. So that would define this proj C prime, the projection of the majority voted C prime, as any classifier in C that agrees with the majority vote of the C prime classifiers on that set X C prime Kp. Okay, so this is going to be useful. And essentially what we'll find is we'll prove lower bounds in terms of the hollow star number and upper bounds in terms of the projection number. Now, generally, the hollow star number is less than or equal to the projection number, which is less than or equal to the dual Helly number. And in fact, if the dual Helly number is finite, then all three quantities are equal. And the paper goes into a lot of detail about scenarios where they're not equal and all these things. So check out the paper for those details. Just to give one concrete example, we show that for the case of linear separators, the projection number is at most dimension plus 2 or VC dimension plus 1. So that's just one example. We have a few others in the paper as well. Okay, so let's start with stating a lower bound. This one at the top here. What this says is if the hollow star number is infinite, then actually no proper learner can do better than 1 over epsilon log 1 over epsilon. So this means the log factor is unavoidable by proper learners whenever the hollow star number is infinite. Now, having infinite hollow star numbers actually seems pretty rare. We give an example of it in the paper, but it's a pretty contrived example. But we also have this second lower bound for finite hollow star number, where you can see it shows up in a log. Now, I think I need to skip the details to save time, but I'll just say like the core of these lower bound proofs, it's all based on the coupon collector argument. You set up some collection of points such that you have to see all of them in order to succeed. And so that's why you get this sort of 1 over epsilon log 1 over epsilon happening. Okay, so now let's move on to the upper bounds. So what this bound says is that there is a proper learner achieving a sample complexity that depends polynomially on the projection number, but there's no log 1 over epsilon anymore. Okay, so this means that if the projection number is finite, then there's a proper learner achieving the right dependence on epsilon, delta, and VC dimension, although we've also got this projection number showing up in the bound. Okay. In the paper, we actually give 2 algorithms achieving bounds like this. I'll just state the simpler one here. It's a recursive algorithm. So first, if the data set's smaller than Kp plus 1, just return any ERM. Otherwise, we'll split the data into Kp plus 1 subsets of roughly the same size and make Kp plus 1 recursive calls, where the ith recursive call has a training set that's the union of all the sets except Si. So you leave out Si. So this gives you a collection of Kp plus 1 different classifiers. And it turns out that you can show the majority vote of those classifiers would have a good error rate guarantee. But since we want a proper learning algorithm, we have to project that majority vote back into the concept class. And that's where we use this projection operator that we defined a couple slides ago. So we don't have time to get into all the details of the proof here, but it's essentially related to the original proof of the optimal pack sample complexity, but modified because we have these this projection operator involved. And in particular, the core of the proof is a kind of conditioning argument that comes up in a lot of these proofs in this literature on the optimal pack sample complexity. Okay, I'll also note that this sample complexity bound is quite specific to this type of proper learning algorithm. And in particular, there are simple examples that show this bound does not hold for general ERM learners. Okay, so that was part 1. Now we'll move into the second part. So we're going to talk about SVM. I'm sure you're all familiar with the support vector machine. It outputs the maximum margin linear separator. And it was known since the beginning that the SVM classifier can be encoded by storing a subset of the data, namely the support vectors. And in fact, there's always a solution that uses at most dimension plus 1 support vectors. So just to abstract that a little, this type of learning algorithm is called a compression scheme. Formally, a compression scheme has 2 functions, a compression function kappa and a reconstruction function rho. The compression function chooses a subset of the data, which we then feed into the reconstruction function to get a classifier. And to be a valid compression scheme, that classifier has to be correct on the full original data set. Okay, so generally, the sample complexity bound for compression schemes of size L, meaning that the kappa function always chooses a subset of size at most L, is sample complexity is at most L over epsilon log 1 over epsilon plus 1 over epsilon log 1 over delta. Okay, so if we plug in specifically for SVM, the compression scheme had size dimension plus 1. So if we plug that in, we can notice actually this is no better than the bound that holds for general ERM learners. Okay, so the question is, can we improve that? So let's notice that the SVM compression scheme has a special property. Namely, if we remove any points that aren't support vectors, we still get the same solution. Generally, we can say a compression scheme is stable if removing any point not in the compression set doesn't change the choice of compression set. Okay, and then what we can prove is for any stable compression scheme of size L, the sample complexity is at most L over epsilon plus 1 over epsilon log 1 over delta. So for stable compression schemes, we can remove that log factor. And in particular, since SVM is a stable compression scheme of size dimension plus 1, this theorem resolves that classic open question. So we've shown here that SVM achieves the optimal sample complexity for learning linear separators. And in fact, this is also the first proof that there is any proper learner for linear separators achieving the optimal sample complexity. And this has implications for other classes too. So for instance, for any maximum class, we know there's a proper stable compression scheme of size VC dimension. So this also proves for the first time that maximum classes are properly learnable with the optimal sample complexity. And just to mention one more example, for those of you familiar with the closure algorithm for intersection closed classes, this is also a stable compression scheme. Now, what's really cool is that the proof of this result is simple enough to fit on one slide. So we're actually going to go through the full proof here. For simplicity, let's suppose the sample size n is a multiple of 2L. And then let's split the data into 2L equal size subsets of consecutive points. And notice that some L of these sets together contain all of the compression points. And stability implies that if you were to apply the compression scheme to just the union of just those L sets, you would get the same classifier as if you apply it to the full set. So in particular, it means that applying the compression scheme to just those L, the union of those L sets, the resulting classifier is also correct on the other half of the data, the other L sets that we didn't pick. Okay, so let's do some simple reasoning about probabilities. What that fact implies is that the probability that the error rate of the compression scheme is bigger than epsilon is at most the probability that there exists some L sets such that applying the compression scheme to their union gives a classifier with error rate bigger than epsilon, but which is also correct in the other half of the data, the other L sets. Now, by the union bound, this is at most the number of choices of L sets, so 2L choose L, times the probability that a fixed choice of L sets has this property, that applying the compression scheme to the union of those L sets gives a classifier with error rate bigger than epsilon, but which is also correct on the other half of the data. Now, but if it was a fixed choice of L sets, the other half of the data is going to be independent of the argument to the compression scheme. So if the error rate is bigger than epsilon, the probability it's correct on that other half of the data is less than 1 minus epsilon to the n over 2. Then just simplify that bound. 2L choose L is less than 4 to the L. 1 minus epsilon is less than e to the minus epsilon. And note that if you set n equal 2 over epsilon, L times log 4 plus log 1 over delta, this whole thing is less than delta. So that's it. That's the whole proof. It's really surprisingly simple given how powerful the result is. Okay, there are some interesting open questions in this work. In particular, it's interesting to consider how the two parts of this work relate to each other. And we also wonder whether maybe the hollow star number might be sort of the right complexity measure for proper learning, and whether proper stable compression schemes might supply some kind of a general solution to the proper learning problem. Thanks.